Hi, hello everyone. Hi, I'm Aslı, Çelik Yılmaz. I'm a researcher here at the LTC under MSRAI, and I'm going to be chairing the session this afternoon. We're going to have three awesome talks, and we're going to start with Kristen, and she's going to be talking about adverbial clausal modifiers in the LinGO grammar matrix. So take it away.
Hi, today I'll be presenting an extension to the LinGO grammar matrix that'll allow for the automatic production of precision grammars that accommodate adverbial clausal modifiers. So this is a little bit less of an NLP talk, so I'm going to start by giving you a background on precision grammars and the grammar matrix in particular. And then I'll discuss the typology of clausal modifiers in the world languages. Introduce you briefly to our syntactic analysis, and then go through our development of the library and our evaluation and error analysis. So precision grammars are bidirectional grammars that parse and generate sentences. But their strength is that they produce very precise syntactic and semantic representations. And in our case, the syntactic representations are in the HPSG formalism, and the semantics are using minimal recursion semantics. The most important thing about these grammars is that they prioritize precision, meaning we care about what proportion of our parses are the right parse, rather than being as concerned with our overall coverage. Uses for these grammars include building grammars for languages where we don't necessarily have enough data for traditional NLP methods, but we do have linguistic information that we can utilize. Linguists use these grammars for hypothesis testing, checking their analyses over a corpus. And these are also useful for finding out what's actually in your corpus. When you run your corpus through one of these grammars, you might find a phenomenon that you didn't realize was there, or you might actually find some inconsistencies either in your data or in your annotation. However, these grammars are very expensive and time-consuming to create. So the LinGO grammar matrix is a starter kit for creating HPSG grammars. Basically, it elicits information from the user about the language and then produces grammars from that. So a quick example. This is the word order page on the customization screen. And it asks the user, what's the basic word order of the language? Is this subject, verb, object, subject, object, verb, and so forth? Do the determiners come before or after the noun? Do auxiliaries come before or after their verbal complements? And then based on the user's input on this page and analyses developed based on the typological literature, a precision grammar is output that can now accommodate that phenomenon. Right now, the grammar matrix includes a wide variety of phenomenon, including word order, morphology, tense, and aspect, but previously it did not accommodate subordinate clauses of any kind. So today we're presenting a library for adverbial clausal modifiers. These are your subordinate clauses that present information like time, purpose, your basic while, because type clauses. And in the world's languages, these manifest in a number of ways, but follow three basic patterns. Typically, clausal modifiers are marked by a free subordinating morpheme, and I'll just use the word subordinator moving forward. And this is a word like when or to in the Japanese example at the top. I can point to that. Another pattern is subordinator pairs, and we see these very robustly in Mandarin, such as the Yinwei Suyoi pair, where you have this because subordinator in the subordinate clause, but then in the matrix clause you have to have this additional adverb. These are also really common in if-then clauses cross-linguistically, if it's easier to think of an English example. And finally, sometimes subordinate clauses are marked just with verbal morphology. So the purposive suffix right here, in this example from Luis Seño, marks that subordinate clause as a purposive clause. In addition to these basic patterns, we also see a very wide range of variation within these clauses. And any given language will probably be marked by a handful of different strategies that utilize these characteristics. So these include the position of the clausal modifier, whether it's before or after the main clause, whether or not there's a pair, whether there's additional verbal morphology. So you might have a subordinator and then also a non-finite verb in the subordinate clause. Sometimes the clause is nominalized or the subject is shared. So it's unexpressed in the subordinate clause, but expressed in the main clause. So this is an example like, I went to the store to buy bread, where I is the subject of both clauses, but unexpressed in the purposive clause. So in order to account for this space and analyze this within the grammar matrix, we introduce two lexical types and two unary rules. And abstracting away from the nitty-gritty HPSG on this slide, basically what we've done is we've created 4 supertypes that account for the basics of each strategy, whether it's a subordinator or morphological subordination. And then onto these supertypes, we can add new features in the subtypes. So to account for all of these characteristics on this slide, we add feature definitions that we can put into the subtypes for each subordinate clause strategy. So for example, we use the post-head feature, which is just a Boolean feature, to constrain whether the clausal modifier goes before or after the main clause. And if it's free to go in either place, then we leave that underspecified. In our development, we use 2 sets of development data. Sorry about that. A quick example of how we map those features onto the customization page for the user is that we use an iterator that allows the user to define as many clausal modifier strategies as they want. So they can have the purposive strategy that just uses the dropped subject and the non-finite in to buy bread. And they can use a different strategy for a because clause, which is marked by a subordinator. And they're free to fill in as many strategies as they need. So when developing, we use 2 sets of development data. Our first stage is pseudo-languages. These are languages with a minimal lexicon that are designed to capture the typological space. So we'll just use a simple language where the nouns are called noun 1, noun 2, and the verbs are called verb 1, verb 2. And then we capture the typological space as best we can by pairing each subordinator type with each feature. So going back to the previous slide, we have all of these feature values that are possible on these subordinator types. And we'll test this add position subordinator lexical type with one of the post-head features. But if we were to actually test all of them, we'd have 1,008 test languages, and that would be really cumbersome, because these aren't just test instances, these are full languages. So at the end of this stage, we expect full coverage, right? We should be able to capture the typological space by accounting for every possible combination of features. However, we don't test each feature value, just every feature type. After that, our second development set is illustrative languages. And at this point, we actually get involved with natural language. It's a bit messier because we're testing interactions that actually occur in real languages, such as subject dropping in the language, various word order patterns. And these interacting phenomena can cause complications that weren't previously tested in the pseudo-language evaluation or pseudo-language testing. So we used 4 real languages that were selected specifically to illustrate a particular phenomenon. So we used Mandarin to illustrate the subordinator pair that I discussed previously. Rukai requires that subordinate clauses be nominalized. German is a V2 language, verb second language, that requires verb final word order in subordinate clauses. So we tested that. And then Wambaya is a language that marks its subordinate clauses morphologically. We tested that as well. Now at this stage, we discovered one phenomenon that's not captured in our library and probably shouldn't be. And this is that subordinate clauses actually have a different case frame on the objects in those clauses. So a nominative accusative language will actually have dative case in the subordinate clause. So we decided that this should actually be treated separately as a valence changing operation in another library that we set aside for future work. So we don't expect full coverage here, as those examples aren't expected to parse. So finally, we move on to evaluation. And at this stage, we test the typological diversity and reliability of our system by testing on 5 held-out languages. This is not just held-out data, but these are languages that we did not consider at all during development. And the way we construct our test suites and grammars is by reading the descriptive grammars written by field linguists that have a lot of very detailed data and prose descriptions. And we develop our test suites from that. These languages were selected in a random manner, but required to be genetically and geographically diverse. So if I pulled 2 Indo-European languages off the shelf, I would put them back so that we represent 5 distinct language families here. We achieved 88% coverage and 2% over generation at this point. And that 2% over generation comes from just one ungrammatical example parsing. And that really shows our fidelity to precision here. As for our error analysis, this actually tells us quite a bit about the library and about the typology of clausal modifiers. So I've broken this into 2 categories, in-scope phenomena and out-of-scope phenomena. We had 1 sentence fail to parse in MOSA 10 due to a constraint in the supertype that shouldn't have been there, should have been added in the subtype. So that's a bug, and it's fixed. Next, we found a bug in the nominalized clauses library, where nominalized clauses had a special head subject rule to allow for that attachment, but did not account for subject dropping, meaning if a nominalized clause didn't have an overt subject, this couldn't parse. And it turns out that's possible in Basque. So we created a rule and inserted that into the grammar to make sure that that sentence would parse if that rule was there. Next, we get to out-of-scope phenomena. And this is really the interesting part of error analysis, because we see what didn't come up in the typological literature that turns out is out there in the world's languages. Our first error came from the same case change issue that we saw in Wambaya. And so I have an example for you here. In this language, third-person subjects are marked with accusative case instead of nominative case in the subordinate clause. And so you see that here. So this wasn't accounted for, and we had 1 sentence that is grammatical fail to parse, and then 1 ungrammatical sentence parse. And that's what led to our 2% overgeneration. The next thing we found in MADI is that subordinators actually can attach to a verb. So in the typological literature, we saw the subordinators attaching either to the sentence on the outside of the clause or to the verb phrase intervening between a subject and verb. But we never saw it intervening between the verb and its object. And in fact, in MADI, it's possible in the sentence, if OP brings beer, he should put it on the shelf. If can intervene between bring and beer. So this is easy enough to add now that we know that it's possible in the world's languages, and that'll be part of our future work. And finally, we found in La Vukaleve that the same pair adverb phenomena that we see in phenomenon, where you have or that you see in Mandarin, where you have a subordinator in the clausal modifier and an adverb in the main clause, can occur where you have a morphologically marked subordinate clause, and you still need an adverb in the main clause. So there was only a brief description of this in the prose in 1 example. So what we would like to do is some further investigation in the typological literature, as well as in that language before adding this functionality to the library, just to make sure. So what we've done today is we've introduced a new library that now accommodates 1 type of subordinate clause in the grammar matrix so that these precision grammars can be automatically produced. Are there any questions? I don't know who's...
What do the grammars look like? Is it like phrase structure rules or XBAR or...
Yeah, so the question is, what do the grammars look like? So we're using the head-driven phrase structure grammar formalism. And this is a lexically driven syntactic framework. And we have a combination of lexical entries and phrase structure rules. Yeah.
what does that bring you up to for how much of English prose are you able to parse now? What rules are you still missing? And do you do all of it and it's just some other languages you don't do? Or?
That's a great question. So the grammar matrix actually grew out of the English resource grammar, which covers 96% of well-edited English text. Maybe it's 94. So that's a very large grammar. We haven't actually tested this on English, like the grammar matrix outputs on English. We are still missing a number of phenomena. A library for clausal complements has just been added, and but there's still more to be done. We don't have relative clauses. We don't have WH questions. So we still wouldn't be quite close to there. But that work has been done on the individual language level. Other questions? Yeah?
Similar question, but what is left to do for any other world languages? You just did the adverbial clause. Is there anything else missing?
Oh, yeah, in terms of phenomena that are not yet in the grammar matrix. We're still missing quite a bit. So what I would recommend you do is go to the grammar matrix page and see what's there. And then you should be able to figure out what's not. But there are lots of new phenomena. Relative clauses, I think, is a next direction. Adverbs themselves, not adverbial clauses, but just adverbs haven't been implemented yet. Yeah.
Yeah, I think I should just give it a pause.
Thank you.
Michael's going to be talking about simple questions nearly solved, a new unbounded and baseline approach. It's a joint work with Luke Zettlemoyer. Take it away.
Hi there. My name is Michael, and I'm presenting, as said, simple questions nearly solved. This was undergraduate research that I did at the Paul G. Allen School. Okay, to give you first a brief overview of my talk. First, we're going to introduce you to the widely used simple questions benchmark. And then we're going to go over the contributions this paper has made onto that benchmark. First, talking about that we actually found that there's an upper bound on this benchmark, and then introducing a simple baseline method that actually gets state-of-the-art results. And then we'll conclude that we found that through our analysis, our upper bound is loose, and that the simple questions dataset is nearly solved. Okay, so first, some background. What is a simple question? So for example, who wrote Gulliver's Travels is a simple question. The reason it's a simple question is because it has one relation, one subject. And a simple question stands for a single relation, single subject factoid question. Why are these questions interesting to look at? Well, they appear often online. Specifically, Microsoft has them a lot in their query logs. We see them popping up in wiki answers, and they're commonly used at voice assistants. Yet, although they're very commonly used, the most popular and largest benchmark by magnitude, the state-of-the-art results on it are only 77%. Okay, so a little bit more background. The simple questions benchmark is the largest simple questions data set with 108,000 examples. Each example has a question that is labeled with a subject, relation, and object. And it has a backend Freebase knowledge graph, which is just a store of facts. And then bringing up an example for that. For example, here's the relation, and this is the Freebase relation for who wrote in this context. And for Gulliver's Travels, the Freebase object has an MID and an alias Gulliver's Travels. Okay, so the first contribution is introducing an upper bound. The example and what's really driving this work is that there's fundamental contradictions in the simple questions data set. For example, who wrote Gulliver's Travels is referring to the TV miniseries Gulliver's Travels, while name a character from Gulliver's Travels is referring to a Gulliver's Travels book. This shows that the linguistic signal in these questions does not provide or provides equal evidence for it being either a miniseries or a book in both cases. It's not clear. Okay, so how do we quantify this and get to an upper bound? So reminder, this is the data set. This is the data that we're dealing with. So the first thing we do is we take a look at the alias, come up with a list of all Gulliver's Travels in Freebase. Similarly, we take out Gulliver's Travels from the question, and we create an abstract relation. And in simple questions, who wrote co-occurs with book written by, film written by, film story by, and other relations. We can take a cross product of these, and these are all possible interpretations of the question that we looked at before, though some of them don't make sense. For example, for Gulliver's Travels, the book, you wouldn't have the relation film. So we just do a filter on them on which ones we actually find in Freebase. And from that, we come up with a list of multiple correct interpretations of who wrote Gulliver's Travels, for which we have equal linguistic evidence for each one of these being correct, yet we only have one ground truth example, which is number 3. Okay, so our results. We find that on this widely used benchmark, 33.9% of the questions have multiple correct interpretations and therefore unanswerable. So in computing the upper bound, we find that not all subject relations are equal. For example, in this case, we come up with the relation film language, but we have an option between 2 subjects. This one right here comes up 4 times in Freebase, while this one right here comes up in 1. And that distribution allows us to set a majority upper bound. So we pick the subject relations which happen most often in Freebase, and we find that the best we can do if we follow that simple baseline is 83.4% on this data set, which is quite close to the 77% state of the art. Okay. Then the second contribution is we're actually able to get state of the art with just standard methods with fine-tuning. So our baseline model is going to consist of 2 neural models. The first one is going to be top case subject recognition, which models the distribution of spans conditioned on the question. Secondly, we're going to have a relation classification model conditioned on the question and span, modeling relation. So to better understand this, here's just an input and output. So we want film story by to have the largest probability given this input. Same up here. So why might we consider top K? Because the first predicted span might not always be helpful. It might not always be in Freebase. So we can do a little bit better by just filtering what is in Freebase and what is not. Some more details. We use standard CRF tagger. We use Viterbi inference, which is standard with a CRF tagger. We use IO tagging, glove embeddings, and grid search for hyperparameter optimization. Similarly here, we use a BiLSTM with batch norm and softmax. We use AMS grad, which is the new version of Atom published recently, fast text, and hyperband for hyperparameter optimization. So the results. So these are the past results. A lot of research has been done on this, and Boards et al. Introduced this paper, or introduced this data set. Oh, one sec. To give you a little bit of history here, the first work done on this was primarily trying to do an end-to-end method. So looking at one model that can both do relation and subject classification. these next two, more recent papers, we're looking at baseline approaches of 2 models. And then these last 3 papers, we're all building custom architectures with 3 models at times for various reasons. So then applying this standard approach and better understanding the data set with fine-tuning, we're able to get 78.1%, which is close to our upper bound of 83.4%. So finally, we want to understand what is the difference here, what work is left to be done. So in understanding this, we first consider our first contribution, and we allow for all correct interpretations to be correct. And that is 13% of our error to start with. Then we found there's a little bit of noise. Finally, for the remaining error, we found out that there's actually further ambiguity. So our initial analysis was very static. So if there's any small changes in the sentence, this didn't catch that ambiguity. So empirical analysis showed that our upper bound is actually loose due to this further ambiguity. And we find that in real model errors, that most of the work left on this data set is actually in low shot relations, where we have less than 10 examples. So in concluding, due to the first ambiguity we found and due to the further ambiguity we found, there's not much more than 4% performance left on this data set, we believe. Secondly, we believe it's largely solved on that simple questions task is largely solved. And this is due to the fact that the remaining errors are mostly due to a lack of data, which is interesting a little bit. Yeah. Okay, thank you.
I guess we can take questions. We have a lot of time. Yeah, go ahead.
It sounds like, I mean, if the upper bound is that poor, it sounds like there's a good reason to say maybe we shouldn't just be returning the top best answer, right? Maybe it should actually be the best 2 or 3, especially if this is to be used by user. I understand why you'd want the top 1 to compare to other systems, but have you considered like maybe making an argument for shared tasks? Like maybe we want to look at the top 3 best answers or something like that.
Mm-hmm. Yeah, for future data sets, it's definitely important to acknowledge the issue that sometimes the top 1 answer, there could be multiple correct interpretations. Yeah.
I have one question here. You mentioned that you could have trained this end-to-end, the relation classifier and the other classifier. Can you elaborate on why you didn't do that? And if you had done it, would you have solved some of the issues that you were mentioning?
Mm-hmm. We didn't. Fundamentally, the purpose or our work was trying to be baseline and standard.
Yeah.
So to integrate both tagging and classification in one model requires more than baseline work. Yeah. So this is just a paper first setting the baseline on this task before thinking about more custom architectures.
Yeah. Do you have any examples that you can show us today? Did you prepare any?
Of custom architectures?
Okay.
No.
Like the questions, like some errors that the model made, and
I don't
would
have.
Have been easier for. I think you showed a few earlier, but that's fine. If you don't have it, that's fine. It was just.
Are you talking about these errors?
Yeah. Yeah.
Okay. I can send them to you later.
Yeah, no, just it would be nice for us to see, what kind of errors that we're missing, false positives maybe.
Yeah. Yeah. Okay.
So I don't know if I'm not getting it. Does this mean this is not really a perfect simple questions archives because there are multiple answers to some of the questions that are listed there? Should you fix the test set so that it is all simple questions?
It's already all simple questions. Just these simple questions tend to contradict themselves with regards to which relation they're looking at. For example, if we're talking about the book Gulliver's Travels, we might ask what is the language of Gulliver's Travels. If we're talking about the film Gulliver's Travels, we might also ask what is the language of Gulliver's Travels. And it's not clear if you're talking about the book or film unless you integrate more complexity into that question. Yeah.
So if it has an ambiguous answer, it's still a simple question?
Yeah, a simple question can have an ambiguous, yeah.
Okay, let's thank Michael again. Okay, so we have Yi from Europe again, Yi Luan. I guess you can introduce the paper yourself.
Okay.
Take it away, thanks.
Hi everyone, I'm Yi. I'm working with Mary and Hannah. I'm going to present our recent work about scientific relation extraction with selectively incorporated concept embeddings. So the reason we are doing this work is that there are countless scientific papers published each year, and and the tools that can manage those scientific knowledge are in great demand. So the task of the goal for this research is that we want to develop information extraction tools using NLP approaches that can support scientific literature. So basically, we want to build like scientific knowledge graph, and also we want to answer some specific scientific search queries. So for example, if you ask the computer, show me the methods for parallel speech tagging, then the computer can give us a list of recommendations of methods that can solve the problem, such as RNN, CRF, and HMM. There are basically two major steps towards the task of scientific information extraction. So the first one is scientific concept extraction, which is first introduced in Zamaraeva 2017. And so the task would be to identify some scientific phrase spans and also classify the phrase span into concept categories, such as method, task, and material. So for example, in this sentence, conditional random fields and name entity recognition will be extracted and classified as method and task. But the focus of this paper would be doing the scientific relation extraction, which is to classify the relations between the pairs of scientific concepts. So for example, in this sentence, we want to know that the relation between conditional random field and name entity recognition is that one concept is used for the other one. So the task is that we want to, given the candidate concept pairs, we want to classify them into scientific relation types. So we introduce 5 asymmetric relations, which is usage, result, model, part of, and topic, and 1 symmetric relation, which is comparison. So the data set we use is Zamaraeva 2018 task 7, which has 500 annotated scientific abstracts from SAR anthology. The main challenge of this task is that the annotation is pretty hard, which requires domain expertise. So this results in like we only have limited training data. So the contribution of this research is that we introduce state-of-the-art neural relation extraction model to scientific domain. And also we propose a novel concept selection layer to the neural structure to mitigate the data scarcity problem. And we obtained the state-of-the-art result in Zamaraeva 2018 task 7. So this is the overall structure of our neural relation extraction model, which has mainly 4 components. So first, given this sequence of text, we want to use a token sequential layer to represent to do a representation for the sequence. And then the representation will be fed into a concept representation layer and dependency sequence layer. And then those representation will be fed into the final relation classification layer and give us the final output. First, the token sequence layer is consists of bidirectional LSTM, which takes the input of word embedding and some feature embeddings. And then the dependency sequential layer is based on this representation. We pass the sentence using some dependency parser, and then we extract the shortest path between the two concepts. And then we decompose the dependency path into two parts. We first find the common ancestor between the two concepts, which is the verb used in this case. And then based on the direction of the relation, we will model forward dependency path and backward dependency path, which represents both the concepts, the dependency path between the concept and the common ancestor. So we would fit in the headward representation of each concept and the common ancestor representation to the backward and forward dependency path. And then we would use the representation, concatenate those tokens as a final representation for the relation. And then we can output the final result. So this dependency representation itself can already give us pretty good result, but something is missing in this structure, that is the representation for the concepts, which can model the whole span of the phrases. A traditional way of doing this is an example in Miwa and Benso 2016, which they automatically learn a weight alpha for each of the individual token in the whole concept. And then they will sum over the whole, all of the tokens within the concept span. The limitation with this approach is that without introducing any prior knowledge of the concept, the automatically learned representation will generalize poorly in the test time. So in order to solve that problem, we propose a new approach, which is concept selection. So we first construct a concept dictionary using the frequent concepts, and then learn a pre-trained embedding for each of those concepts. And then given a new concept, we will look up through the concept dictionary and see if there is exact match for the phrase. So if there is one exact match for the phrase, we will use the pre-trained embedding directly as a concept embedding. But if there isn't an exact match, we will decompose the phrase into some sub-n-grams. So for example, here, pronominal, say the concept candidate is pronominal anaphora resolution. But there is no exact match in the concept dictionary. So we would decompose the whole phrase into bigrams and unigrams. And then we look up those bigrams and unigrams in the dictionary and find some matches. So here is the resulting candidates that we could find, which is anaphora resolution, and anaphora. And then we will use these candidates together with a empty, with a dummy vector, d-empty, to construct a vector of candidate sets. And then, in order to learn the final representation, we need to selectively combine all those representations. So in that case, we use attention mechanism to learn a weight between each of these embedding and the representation in the sequential layer. And then we will sum over all the candidates to get the final embedding. In order to get the prior phrase knowledge, we would first extract all the concepts in large-scale scientific corpus using state-of-the-art scientific term extractor proposed in 2017. And then we use word2vec to train all the frequent concepts, and then construct this concept dictionary. The dataset we use in this task is Samuel 2018, task 7, which has 3 subtasks. So the first subtask is relation classification, which we assume that concept pairs and relation directions are given. So we need to choose between the 6 defined relations. And the second task is relation extraction, where given all the concepts, we need to identify if the relation exists. And this is a binary classification task. And the third task is a relation extraction and classification task. And so we need first to extract those relations and then classify them into 6 relations together with their directions. So the external data set we use to train this concept embedding is semantic scholar corpus, which has 110K abstracts, and the ACL anthology reference corpus, which has 22K full papers. So here is the results. So we can, our system got the best result in subtask 2.1, and we also did a good job in other 2 tasks. So team 1 did a little bit better than us, but they used like more supervised data. We also perform ablation studies by removing some of the components of the neural network. So we first, sorry. So we first remove the dependency layer, which can give us, which we could see that the F1 score decreased greatly. And then we remove this concept layer, which also results in a worse, slightly worse F1 score. And we also perform the baseline method, which is the weighted sum of the tokens. And this one also like didn't perform very well. So the conclusion is that the dependency information is very important in this task because we don't have a lot of data, and some external knowledge from the dependency parser is very important. And also the baseline method decreases the performance. We think like this is because like it introduced some of redundant parameters. And we also find out that replace the span representation with selected pre-trained concept layer would significantly improve the performance, which can give us the best result of 44.1. So the summary of this research is that we introduced a new neural relation extraction model to scientific domain, and we propose a novel concept selection layer to the neural structure that can leverage unlabeled data. And also we obtained the state-of-the-art result in September 2018, task 7. Yeah, so that's it. Any questions?
I have one question.
Okay.
So you mentioned about if you go to the experiments, so you mentioned the T1 having a better result, and you mentioned that they use more unlabeled or labeled data?
Labeled data.
Oh, okay.
Yeah, so so there are separate data sets for different tasks, and they're combining those data.
Oh, I see.
Yeah.
Because like you're showing that the unlabeled data actually really helps, so I was just under the impression.
Yeah, they are using more supervised data, training data. So
got it.
yeah.
Okay. Okay. Is there any other question? Okay. Yeah.
Thank you.